So in the last lecture we talked about composing functions. So what happens when we do one function after another? And we asked ourselves, how does that interact with the properties of injective and surjective? And we found that actually compositions play really well with those properties. It conserves injectiveness and it conserves surjectiveness and it conserves bijectiveness. And what I want to do now is think about what happens, how can we use those properties to understand when we can do a function to get from a set A to B, and then undo that function using an inverse function to get back from B to A to what we started with. So given an input, do function f to it to get an output in the set B. And then when is there a new function g that will take me back to the original set A and back to my original input? So inverting a function, undoing a function. Okay, so that's the topic of today's video. So inverse functions. Now we have to sneak up on this a little bit slowly because we have this thing called one-sided inverses where one way around things work and the other way it doesn't. So let's start off with two functions f and g. So f takes us from A to B and g takes us back from B to A. And we can ask, well, what happens if I do g after f and what happens if I do f after g? So let's look one way around. So if we do g of f, so we do f first to take us from A to B, and then we do g to take us from B back to A. Well, if that composition is just the identity function, so that g of f of little a is little a, so just the identity, then we say that g is the left inverse of f. So that's because g here is on the left when we write from left to right, as we typically do. So if g of f is the identity, then we say that g is the left inverse of f. Now similarly, if we do this the other way around, so we start here with an element of b, we apply g to it to get an element of a, then we apply f to take us back to b. So we start at b, go to a using g, and then back to b using f. So f of g, if that thing is the identity, so composing it the other way around, then we say that g is the right inverse of f because, well, as we write it down here, it's on the right-hand side of f rather than the left-hand side of f. Now, if g is both a left inverse and a right inverse, then we say it is an inverse of f. Because at this point, we don't actually know that f has only one inverse. We don't know that it may have multiple inverses. In fact, we have to prove that if f has an inverse, that it's unique. And so that's what we will do, but we'll do it in a moment. So at this point, we only know that if g is both a left and right inverse, so that composing either way around gives you the identity, then we'll call it an inverse of f. And then a little bit will prove that if an inverse exists, then it is unique, which means that we can sensibly talk about the inverse and denote it by f to the minus 1, using that same notation as preimage, which is a bit annoying, but it's the notation we're stuck with. So when we know it's an inverse, this thing that we use to denote the preimage will denote the inverse function. So let's see some proofs here or some theorems about this, or even actually just an example showing why we need this notion of one-sided inverses. So here's an example of a left inverse which is not a right inverse. So let's take the functions f and g defined by these diagrams below. So f maps from A to B and g maps from B back to A. And to put a handle on things, I've called these elements 1 and 2 and these 4, 5, 6. So 4, 5, 6, 1, 2. Okay. So notice if we do which way around, let's see, we're going to do f first and then g, then f takes 1 to 4, g takes 4 back to 1. F takes 2 to 5, g takes 5 back to 2. And so g of f of 1 is 1, g of f of 2 is 2. So g of f is just the identity on this starting set, so g is the left inverse of f. But then if we try the other way around, well, notice that if we do g first, g takes 4 to 1 and 1 to 4 using f. G takes 5 to 2 and then f takes 2 to 5. So we see that g of f of 4 is 4 and g of f of 5 is 5. So far so good. But if I take 6, then g maps 6 to 2 and then f maps 2 to 5. So f of g of 6 is 5, which is not 6. And so f of g is not the identity on that set, so g is not a right inverse. Okay? And here, what's actually causing us problems is the fact that g isn't injective. It's the non-injectiveness of g which is to blame. And you can construct a very, very similar example, which maybe will make a homework problem, that shows that a right inverse, or functions which are a right inverse but not a left inverse, and here will be non-surjectiveness, which causes problems. So it's easy to make a similar but sort of twinned example to this one to show that you can have a right inverse which is not a left inverse. So that's why we need this notion of left and right inverses. We're sneaking up on the idea of a full inverse. So, well, when do we know that these one-sided inverses exist? Well, you can prove that if f has a left inverse, if and only if, so remember that's actually a biconditional here, if and only if f is injective. And f has a right inverse if and only if f is surjective. And so it's really this injectiveness, surjectiveness that's tied together with when inverses exist. And you can see, well, if it's bijective, then it will have a left and a right inverse. And the proofs of these statements make really good exercises, but I'm just going to do the forward implications here. And again, maybe the reverse implications will be in homework or in class. They may be a little bit more involved doing reverse implications. So let's look at the first one. If f has a left inverse, then it's injective. So that was the forward implication. The reverse implication, maybe you'll see in homework or in class. So let's assume that f has a left inverse, namely g. So that we know g of f of x is just x. Well, let's take 2 points in A, A1, A2, so that their images are the same. So this is our steps towards proving something's injectors. If the images are the same, then the points have to be the same. Okay, so that is, if f of x1 equals f of x2, then x1 equals x2. That definition of injectiveness. So we're going to take a1 and a2 in A, so that their images are the same. Well, then we can apply g to both sides of this equation, and because those are the same inputs into g, we know that g of f of a1 is g of f of a2. But we know g is a left inverse, so we know that this holds, and so this is just a1, and this is just a2. So a1, okay, there's a little bit of a typo here, that should be a1 equals g of f of a1, and that's the same as g of a2, which is a2, and so we know that a1 equals a2, and so f is injective. So the existence of a left inverse gives you injectiveness. And we can make a similar flavoured proof to show that if it's a right inverse, then it's surjective. So let's assume that f has a right inverse, again we'll call it g, so that we know that f of g of y is equal to y. So remember it's a right inverse, so we have to compose the other way round. So let's take some element b and b, then we have to find something that maps to it. So let's set a as g of b. Remember g takes us from the set b back to the set a. Then f of a is f of g of b, which is equal to b, because of this right inverse property. And so, given some b, we've found an element of a, so that f of that element is equal to b. All thanks to the right inverseness, and so f is surjective, because given any b in b, we found a in a, so that f of a equals b. So giving us surjectiveness. Okay. Now, as I said, the converses of these statements are a little bit more involved. We might do them in class, maybe in homework, sort of stepped out neatly. Okay. Now, when we know that we have a left inverse and a right inverse, we can ask ourselves, well, what are the relationships between those functions? And so if f has, mapping from a to b, has a left inverse and a right inverse, then those functions actually have to be the same. So there's one function which is going to be doing both. So in particular, if we let f map a to b and g be its left inverse and h be its right inverse, well then we know g of f is the identity on a and f of h is the identity on b. Okay, that's exactly this left inverse property, right inverse property, giving us this and this. Then, well, we can manipulate things around to show that g equals h. So in particular, we know that g, well, we can write g as g composed of the identity. But then we know g, well, we know the identity is just f of h, that's up here, that's that right inverse property. Then we know we can write g as g of the identity on b, which is g of f of h. Then we can use this associativity of compositions that we didn't prove, we did state, because proving it's quite tedious, to put the brackets the other way around to group this as g of f of h. Well, g of f is just the identity on a, so this is the identity composed with h, which is just h. So we've shown that g and h are actually the same function. Okay, so if a function has both a left and a right inverse, that function has to be the same. Now, because of this, we can put all of these things together to decide when a function actually has a full inverse. So we've put all of these ingredients together now. So if we have f as a function from a to b, well, that function f has an inverse if and only if f is bijective. And further, that inverse, if it exists, is actually unique. So that's why we can talk about the inverse of a function rather than an inverse. So let's assume, it's actually three things to prove here. Let's assume that f has an inverse g, so we're going this way. Since G is both left inverse and right inverse, well, we can use one of the lemmas we just proved just a couple of slides ago to say, well, since it's left inverse, F is injective, and since it's right inverse, it's actually surjective, and so F has to be bijective. And that's just using one of the lemmas that we did just a slide or two ago. Okay, so that's proving that forward implication. I should draw a double arrow there. Now to do the reverse implication, well, let's assume F is bijective. Well, since F is injective, because it's bijective, it has a left inverse. And since it's bijective, we know it's surjective, and so it has a right inverse. Those one-sided inverses we just proved a slide or two ago are actually the same function, and so that function is an inverse. Okay, so we've proved both of these implications here in this if and only if, and it only remains to show that that inverse is unique. So we can actually recycle some of the work that we did just back here, use very, very similar reasoning to say that, well, if G and H are both inverses of F, well, then we can write G as G composed with the identity, which is G composed with F of H, because F of H is the identity, which again we can group it this way round, because we know that this is the identity on B. Compose it this way round, that's the identity on A, and so that's just H. And so we've shown that G equals H, and so that inverse function is actually unique. Okay. Now, let's actually just look at a quick example of this. So we've seen from previous lectures that the function from the reals to the reals defined by 7x minus 3 is bijective, and so we know it has an inverse. Okay, now, well, actually that's all we have to state. Previously we showed it was injective and surjective, and so bijective, by the previous theorem, that just tells us the inverse exists. Now in this case, this function is sufficiently clean that we can actually write out the inverse quite explicitly. So the inverse function taken from the reals to reals is defined by f minus 1 of y is y plus 3 over 7. Now we saw that because that was what we used to prove surjectiveness, and indeed there's a connection there. That if we are going to prove surjectiveness by explicit means like that, then what we need is actually an inverse function to plug in there. But now, all we need to do to verify that this is actually the inverse, well, since this function is bijective, it's sufficient to just check that it's either a left inverse or a right inverse. So let's check this left inverse property. Excuse me, I will keep that in the video just to show you how authentic these videos are. The f to minus 1 of f of x is f to minus 1 of 7x minus 3, because that's just f of x, which, just do a little of algebra here, reduces to x as required. And it's enough to say, hey, it's a left inverse. Because this function is bijective, we know it's a left inverse, it's going to be an inverse, which is going to be a right inverse. So we only need to check one of these compositions. And so we've shown that this thing really does have explicit inverse given by this quantity here. Okay, let's stop there.